Hello viewers, in today's session we are going to discuss another important problem from domain of functions, and here we are going to find out the domain of this function f of x, that is equal to 1 over square root of x square minus 1, and here we have sine inverse x minus 1 over 2 plus logarithm of x minus 1, right? So here we'll see how we can find out the domain of functions where we have a combination of functions. So here we have the product of these two functions, and then this function, that is the natural log of x minus 1, is added to the product of these two functions, right? So here we'll first separately find out the domain of these three functions, that is 1 over square root of x square minus 1, and then sine inverse x minus 1 over 2, and then natural log of x minus 1. And then by the concept of intersection of domains, we can easily identify the common domain or the common values of x which satisfies all these three functions simultaneously, right? So let us start. So let us first assume that this function is g of x, that is 1 over square root of x square minus 1, and let us take this function as h of x, that is sine inverse x minus 1 over 2, and let us take this function as p of x, that is natural log of x minus 1, so that we can now write this function f of x as g of x times h of x plus p of x, right? Okay, now let us assume that the domain of this function g of x is d1, the domain of this function h of x is d2, and the domain of this function as d3, right? And the domain of this function f of x as d. So the domain of this function f of x, that is d, can be written as d1 intersection d2 intersection d3. That is, we have to identify the common interval which satisfies this function, that is f of x, or the common values of x for which this function is defined, right? So let us find out the domain of the function g of x, h of x, and p of x one by one. So let us first take g of x. Now see, here in the denominator we have square root of x square minus 1, and clearly this function g of x is defined for those values of x for which x square minus 1 should be greater than 0, right? Because x square minus 1 should be positive, because x square minus 1 is inside the square root sign, and inside the square root sign we must have a positive quantity, because the square root of positive quantities are defined in the set of real numbers. And if x square minus 1 is a negative quantity, then the square root of negative numbers are defined in the set of complex numbers. But here we are talking about the real numbers, so x square minus 1 should be greater than 0. So here we can now write this inequality as x square is greater than 1, right? And we can also write it as x square greater than 1 square. So now we have to find all the values of x which satisfies this inequality. So here we'll make use of an important result, and the result it goes like this. If we have say x square greater than a square, then the value of x belongs to this interval, that is minus infinity to minus a union, and here we have plus a to infinity, right? And if we compare this inequality with this one, then the value of a is 1, right? So the solution of this inequality is given by minus infinity to minus 1 union 1 to infinity. And let us represent these values of x on the real number line. So here we have the real number line, minus infinity, here we have plus infinity, here we have minus 1, and here we have plus 1, right? So x belongs to minus infinity to minus 1. So here we have this region, and then we have 1 to infinity. So here we have this region, right? So here minus 1 and 1 are not included, because x is equal to 1 gives us 1 square minus 1, that is 0, which can be discarded, because then the function g of x is not defined. And similarly, when x is equal to minus 1, then minus 1 square is positive 1, and 1 minus 1 is 0, and again the function g of x is not defined. So we have to discard minus 1 and 1. So the domain of this function 1 over square root of x square minus 1 is given by this region, that is from minus infinity to minus 1 and 1 to infinity. So we can now write here d1 is given by minus infinity to minus 1 union 1 to infinity. And here we have used the direct result for the solution of this inequality, that is x square greater than a square, and the solution is x belonging to minus infinity to minus a union a to infinity. So let us now find out the domain of h of x. So here we have the inverse sine function, that is sine inverse x minus 1 over 2, right? So here I will make use of the concept of inverse trigonometric function, that is the function sine inverse theta. The range of sine inverse theta belongs to this interval, that is minus pi by 2 to pi by 2, provided this theta it belongs to the interval minus 1 to 1, right? And if we compare sine inverse theta with this one, then the value of theta is given by x minus 1 over 2. So x minus 1 over 2 must belongs to this interval, that is from minus 1 to 1. So from here we can form the inequality, that is x minus 1 over 2 should be greater than or equal to minus 1 but less than or equal to plus 1. So now we have to solve this inequality. So let us multiply throughout this inequality by 2. So here we have minus 2, then we have x minus 1, and here we have 2. So now let us add 1 throughout so that we can get rid of this negative 1. So we have minus 2 plus 1, here we have x, and here we have 2 plus 1. So minus 2 plus 1 is minus 1, and here we have 2 plus 1, 3. So sine inverse x minus 1 over 2 is valid for the values of x for which x belongs to this interval, that is minus 1 to 3. So the domain of the function h of x is given by this interval, that is minus 1 to 3. And let us represent this interval on this real number line. So here we have minus 1 and here we have 3. So 3 lies somewhere here, right? So now the region that is from minus 1 to 3, where minus 1 and 3 both are included, right? So this domain can be represented like this. So here we have minus 1 to 3, and here 3 and minus 1 both are included, right? And in the first case, that is when we have found out the domain d1, then we have discarded minus 1, so we'll discard minus 1 later on. So but when we consider only sine inverse x minus 1 over 2, then the domain of sine inverse x minus 1 over 2 is from minus 1 to 3. So this reason it represents the domain of h of x. So now let us find out the domain of the function p of x, that is natural log of x minus 1. Now see, here we have natural log of x minus 1, and the valid values of x for which the natural log of x minus 1 is defined is given by x minus 1 should be greater than 0, right? So x should be greater than 1. So here x minus 1 should be a positive quantity, because the natural log of positive quantities are defined in the set of real numbers, and the log of negative quantities are defined in the set of complex numbers. So here x minus 1 should be greater than 0. So solving this inequality, we have x greater than 1. So this implies that x should belongs to this interval, that is from 1 to infinity, right? So the domain of this function, that is d3, is given by 1 to infinity, and let us represent this interval, that is 1 to infinity, on this real number line. So here we have 1 and here we have infinity, so we'll go like this, right? And remember here 1 is not included, because if x is equal to 1, then we have 1 minus 1, so natural log of 0, right? So we'll discard x is equal to plus 1. So now we have obtained the domains d1, d2 and d3, and we have represented these domains on the real number line, right? And now from this diagram we have to identify the domain of the function f of x, which is given by the intersection of these three domains, right? So let us make use of this diagram to get the common values of x for which this function f of x is defined. So here the domain d1 is from minus infinity to minus 1, and union 1 to infinity, and d2 is from minus 1 to 3, and d3 is 1 to infinity. Now from this diagram we can easily conclude that the common region is given by this one, that is from plus 1 to plus 3, right? Because this portion and this portion are common to all the three domains. So here the domain of the function f of x is given by plus 1 to 3, and remember here plus 1 cannot be taken, because here plus 1 makes x square minus 1 is equal to 0. So we can here write the domain of this function f of x as 1 to 3, but here 3 is included, right? So the common region which is identified here from the domains d1, d2, d3 is from 1 to 3, and here this interval is open from the left, that is x is equal to 1 is not included, and here it is closed from the right, that is x is equal to 3 is included. So here this region, that is plus 1 to 3, is common to these domains d1, d2 and d3. So the intersection of these three domains is given by this interval, that is from 1 to 3, and all the values of x which belongs to this interval, that is 1 to 3, it satisfies or it defines the function f of x. So here this interval can also be expressed like this, that is x is greater than 1 but less than or equal to 3. So either we can represent the domain of f of x like this, x greater than 1 but less than or equal to 3, or x belonging to this interval, that is 1 to 3, open from the left and closed from the right. Hello viewers, in today's session we are going to discuss another important problem from domain of functions, and in this session we are going to find out the domain of this function f of x is equal to cosine inverse, and here we have natural log of x minus 2, right? So here we'll try to find out the domain of this function where we have the inverse trigonometric function, that is cosine inverse, and here we have the logarithmic function. So let us take natural log of x minus 2 as theta. So here we'll make this assumption, that is theta is equal to natural log of x minus 2. So now we can write this function f of x is equal to cos inverse theta, right? Okay, now from inverse trigonometric functions we know that the range of cosine inverse theta is given by this interval, that is 0 to pi, provided this theta belongs to the interval that is minus 1 to 1. So the principal value branch of cos inverse theta belongs to this interval, that is 0 to pi. This is the closed interval, and provided theta belongs to minus 1 to 1. So we can also write this expression as theta greater than or equal to minus 1, and here we have 1. So now we can replace this theta by natural log of x minus 2. So here we have minus 1, then we have natural log of x minus 2, and here we have 1. So now we have this inequality, right? And we have to solve this inequality for x, right? Okay, so now here what we will do, we'll take all these three numbers to the power of e, where e is the exponential number. So in order to solve this inequality for x, we have to raise these three numbers to the power of e. And remember, the function that is log x to the base a is always an increasing function for all values of x in its domain when we have a greater than 1. And here we have the natural log, and it implies that we have the base of the logarithm as e, and e is greater than 1, right? So we can raise these three numbers to the power of e without disturbing the direction of the inequalities. So we can now write e raised to minus 1, and here we have e raised to natural log of x minus 2, and here we have e raised to 1. So the purpose of raising these three numbers to the power of e is that this expression, that is e raised to natural log of x minus 2, is equal to x minus 2, because we know this result, that is m raised to log of p to the base m is always equal to p if m is greater than 0 and m is not equal to 1. And here we have e, because the base of this log is e, so the value of m is e, which is obviously greater than 0 and it is not equal to 1, and the value of p is x minus 2. So e raised to natural log of x minus 2 is equal to x minus 2. So here we have e raised to minus 1, and here we have simply x minus 2, and here we have e. So now let us add 2 throughout this inequality. So we have e raised to minus 1 plus 2, and here we have x minus 2 plus 2, here we have e plus 2. So this is e raised to minus 1 plus 2, and here we have x, and here we have e plus 2. So now this inequality suggests that x is greater than or equal to e raised to minus 1 plus 2, but less than or equal to e plus 2, right? So now let us see this log term here. Here we have a log of x minus 2, right? So natural log of x minus 2 is defined for all values of x for which x minus 2 should be greater than 0, because here we cannot have a negative number, because the log of negative numbers is not defined on the set of real numbers. So we must have x minus 2 should be greater than 0, that is x should be greater than 2. So we have to now merge this inequality with this one, that is we have to identify the common region between this inequality and this inequality, right? So here natural log of x minus 2 is defined when x minus 2 is greater than 0, that is x is greater than 2. So now let us take the help of the real number line. So now here we have the real number line minus infinity and plus infinity, right? And here the first condition is that x should be greater than 2. So here for simplicity, let us represent the numbers like this, that is 0, 1, 2, 3, 4, and 5, right? And here x is greater than 2, and here it is important to note that x is not equal to 2, right? So log of x minus 2 is not defined for x equal to 2. So we have to first discard x is equal to 2. So x greater than 2 implies that we have the interval that is 2 to infinity. So here we have this reason for this interval, that is 2 to infinity, and here x is equal to 2 is not included. Now let us represent this inequality on this real number line. So here we have x greater than or equal to e raised to minus 1 plus 2. So here we can write 1 over e plus 2, and here we have x, and here we have e plus 2. Now we know that the approximate value of e is equal to 2.718, right? And the value of 1 over e, 1 over e can be written approximately as 0.3678. So we can divide 1 by e, and we can get the approximate value as 0.3678. So here 1 over e is 0.3678, and here we have 2, and then we have x, and here we have 2.718, and here we have 2, right? So adding these two numbers, we have 2.3678, and here we have x, and here we have 4.718. So our x, it lies between these two numbers, including the endpoints, right? So 2.3678, it lies somewhere here, right, between 2 and 3. And this number 4.718, it lies somewhere here. So we have this reason, that is this inequality can be represented like this, including both these points, right? So 1 over e plus 2 is approximately equal to 2.3678, and e plus 2 is approximately equal to 4.718. So the representation of this inequality on the real number line is given by this line. So now we have to identify the common region between these two regions. That is first from 2 to infinity where 2 is not included, and from 1 over e plus 2 to e plus 2. So this number is 1 over e plus 2, and this number is e plus 2, and from these two regions we can easily conclude that this portion, that is this interval x belonging to 1 over e plus 2 to e plus 2 is the region which is common to these two inequalities, right? So the domain of this function is given by this reason. So this interval which is closed from both the ends gives us the domain of f of x, and the domain is given by this interval 1 over e plus 2 to e plus 2.